Welcome to 6.03 Calorimetry Lab. In this recording, we will walk you through the basics of the lab and go through a calculation problem. In the experiment, you will do very similar calculations as to what we are about to do. Please make sure that you do get the data by doing the actual lab. You will heat the metal, transfer it to a calorimeter that currently has cool water. Please be sure to record all your measurements carefully as you will use your data to do the calculations for your lab report. In the beginning, you are going to heat the metal to about 100 degrees Celsius. The metal is over here in this tub on the right hand side. And then you are going to transfer that really super hot metal into this calorimeter. Has cool water in it already. In the calorimeter, the hot metal is going to transfer its heat to the cool water, and eventually both the metal and the water will reach the same final temperature. In order to do the calculations for this lab, which most students have severe difficulty with, we must understand what is actually happening in the lab. If you truly don't understand what's happening, the calculations are not going to make any sense and you're going to be lost. When we do the calculations, we must think about what is happening in the calorimeter only. Right now, I'd like you to pause this recording and think about, in this calorimeter, what is the system, what are the surroundings, and then explain what the value of Q for each will be. The system is the metal. The surroundings are the water. The value of Q, since the water is gaining energy from the hot metal, water is going to have a positive Q value. Since the metal is hot, it's going into a cooler substance, it's going to release its energy, therefore it's going to have a negative Q value. If you are confused about the value of Q and positive and negative, endo and exothermic, please go back and watch the regular 6.03 recordings. The metal will transfer its heat to the water. Now remember, this is only in the calorimeter. The water is going to increase temperature, right? Because it starts off cool, you put a hot piece of metal in it, of course the water is going to increase a little. It's going to gain heat from the metal, therefore the water will have a positive Q. The metal is going to cool off, it's going to decrease temperature because the metal was super duper hot when we put it in the calorimeter, and then it cools off because it's transferring its energy to the water. The metal is losing heat, its value of Q is going to be negative. The metal and the water will eventually reach the same final temperature. Now, an important relationship that we see from the lesson is Q of the surroundings equals negative Q of the system. For our investigation, it is Q of water, water's our surroundings, equals negative Q of the metal. This is because of the law of conservation of energy. Law of conservation of energy says that energy can neither be destroyed nor created. Therefore, if something loses energy, such as our metal, something has to gain it, such as our water. Pause this recording. Try this, get as far as you can. Even if you just make a list of what you're given, be very careful. You might want to make a data table, kind of list what information they give you about. Is it the temperature of the metal? Is it the temperature of the water? Is it the mass of the metal, the mass of the water? You must be very careful and very specific. Here's our formula. Our question's asking us to solve for the specific heat of the metal. If we use the specific heat formula, we get Q of the metal equals mass of the metal times the specific heat of the metal times the change of temperature for the metal. With the data that we've been given, we have a problem. It doesn't tell us what the specific heat of the metal is because in fact it's asking us to solve for the specific heat of the metal. It doesn't tell me how much heat the metal lost. I have one algebraic equation with two unknowns, and as you know from algebra class, that's impossible. But have no fear. Is there a way that we can get one of these values and then use this formula? You betcha. There is a way that we can solve for Q of metal. Remember, Q of water equals negative Q of metal. So is there a way we can figure out how much heat the water gained and then in turn know how much heat the metal lost? And then we can use this formula to solve for C for the metal. And that is exactly what we are going to do. We must solve this by doing two different calculations. This is the same as in the lab. It's calculation number 1 and calculation number 2. Number 1, how much heat did the water absorb? So we're going to use all the values for water. Please be careful. A lot of students get very confused and they end up using wrong information and they get a wrong answer. You must use the information about the water in the calorimeter. Once we solve for the Q of water, we know that the Q of water equals negative Q of the metal because of the law of conservation of energy. Now we can plug it into this formula, rearrange, and solve for the specific heat of your metal. So hit pause real quick and fill in that information from the problem. I have all the information in the table now. In the data, it had the initial temperature of the hot metal was 100.5 degrees Celsius. It told us that we put 21 milliliters of water into the calorimeter. The water was at a temperature of 22.1 degrees Celsius. The metal had a mass of 14.6 grams. At the end of the experiment, the water and the metal had the same final temperature of 26.4 degrees. So in order to calculate how much heat the water absorbed, we need the specific heat formula. And notice my subscripts, I have water. We have to use all the information for water. I don't have mass or specific heat of water, do I? Think back. Remember from the 6.03 recording in the lesson, it's given to you in the lab report too. The mass of water was not given. However, the volume of water was. Density to do that conversion. Density is something you guys have been studying since elementary school. So now it's time to apply all that gathered knowledge. So with our mass, we know that 21.0 milliliters of water was put into the calorimeter. The density of water is 1 gram per milliliter, which gives us 21 grams. Plug in all of our values for the water. 21 grams. The specific heat of water is 4.184 joules per gram degree Celsius. Remember your temperature change. Your delta temperature means final temperature minus initial temperature. 26.4 degrees Celsius minus 22.1 degrees Celsius. And multiply that, you will get a final answer of 378 joules. You'll notice that your grams will cancel, your degrees Celsius will cancel. So the water absorbed 378 joules of energy. What is the specific heat of the metal? Well, we know that Q of water equals negative Q of the metal. We know that the water absorbed 378 joules of energy, therefore the metal had to have lost 378 joules of energy. The question asks for specific heat though. It is C that we're solving for. Now we know what the Q of metal is. And plug in all my values. Negative 378 joules. This is the mass of our metal. My final temperature of the metal is the same final temperature as my water was. The initial temperature of my metal was so much higher. Do this subtraction. You should get negative 74.1 degrees Celsius is that difference. And now I'm going to take that number and multiply it by 14.6. Just, kind of clean up this algebra problem a little bit. Negative 1081.86. Just using algebra. All we're doing is algebra here. To get C by itself, we have to take negative 378, divide by negative 1081, and we get 0.349 joules per gram degree Celsius, which is the specific heat of our metal. We don't know what metal we've been using so far, huh? When you get into the lab, you're going to have part 1 and part 2. Part 1, they're going to tell you what metal you have. Part 2, you're going to have an unknown. So we're going to actually go through the next calculation, just like you're going to do in part 2. So using the table below, what is the likely identity of our metal? Well, our metal's specific heat, we calculated it to be 0.349. So we look at our table, and which one is closest to that? I'd have to say rubidium. The percent error is the experimental value minus the actual value divided by the actual value. And we do have these lines here. We're going to take the absolute value of this, and then we're going to multiply by 100%. Now we identified our metal as rubidium, which means the actual value is 0.36. What is the experimental value? You're right, the experimental value was 0.349. That is what we solved for in the lab. Our experiment gave us this value. So plugging into our formula, we get our experimental value minus our actual value divided by our actual value, multiplied by 100%. and our percent error is 3%. That is how you do the lab. Now, like I said, there's going to be two parts. Part one, you're given a known metal like copper or aluminum. You're going to go through the same two calculations though. You're going to calculate this heat gained by the water. Q of water equals negative Q of metal, and then you're going to solve for the specific heat of the metal. Part two, same thing, you just don't know the identity of the metal, but that's okay. You're going to go through the same two calculations, and then you're just going to figure out which metal you have and calculate your percent error. I hope you have a great time in the lab, and I hope this helped you. So here's a quick problem. You have the formula here. It's just an algebra problem. I know we have not gone through one yet, but I have full confidence that you guys can do this. Make a list of what you're given, then pause this recording and get as far as you can. Welcome back. I have listed here everything that we need to know. We have mass equals 25 grams, our initial temperature. I have a subscript of an I here that equals 22 degrees. It told me that it's going to increase from 22 degrees, which means that's my initial temperature. My final temperature is 29.7 degrees Celsius. And it said that I added 684.4 joules of energy. And now when I look at my formula, the only thing I don't know is C. Therefore, I have to rearrange to get C by itself. So our specific heat, I'm just going to plug in all the values. Okay, now what I'm going to do is I'm going to go ahead and multiply the bottom. And now I'm going to take the bottom and divide that into the top. And notice that I have a very high specific heat capacity, which it told me in the problem that it has one of the highest of any pure metal. Practice number 2. Please pause this recording, make your list of what you're given in this problem, write down the formula, and get as far as you can. When you're ready to resume, hit play. Here is our list of what we were given in the word problem. I like to make a list of what we're given. It makes the word problem so much easier. We were given the value of Q, which is our joules. That's our unit of Q. We're given our mass. We were given our final temperature and asked to solve for our initial temperature. And we were also given the specific heat, which is C, of the metal. The formula we need is our traditional specific heat formula. Q equals mass times specific heat times change of temperature, all of the same substance. However, we are solving for the initial temperature. Therefore, I'm going to have to expand that to say final temperature minus initial temperature, because I am solving for that initial temperature. Now what we can do is just plug in our values, Q, M, C, and TF, and that is what we get. 2492 joules equals our mass multiplied by our value of C multiplied by our change of temperature, but be careful because we only have this as final temperature right here, and then we have to keep TI the same. The way that I like to do this is I'm going to go ahead and multiply these first two numbers. So 124.6 times 1.25 gives me 155.75. Notice that my grams will cancel, therefore the unit of that is going to be joules per degree Celsius, because that's the only thing that has not canceled for those two. Now what I'm going to do is I'm going to move this over to the other side. So 2492 divided by 155.75 joules per degree Celsius. When I do that, my joules cancel. This cancels. And I get 16 degrees Celsius equals 130 degrees Celsius minus my initial temperature. Since this temperature here is there, we can subtract it from both sides, and then that will get rid of that value, and that gives us a negative 114 degrees Celsius equals negative initial temperature. Initial temperature is supposed to be a positive T. The variable has to be a positive, so we just change the sign on both and we get 114 degrees Celsius. So this mercury started off at 114 degrees Celsius. It added 2492 joules worth of heat, and then it reached a final temperature of 130 degrees. Here are some basic vocabulary terms that we need to understand for this lesson. The law of conservation of energy states that energy can neither be created nor destroyed. Heat that is lost or gained by the system must equal the heat lost or gained by the surroundings. One of the values of Q, that's our heat, remember Q is heat, one of the values of Q will be positive, whichever one gains. If the system gains or the surrounding gains, that will have a positive Q. The other will be negative. Whichever of the system or surroundings has lost heat will have a negative value of Q. In 603, we're going to actually apply this concept of specific heat in a new laboratory technique called calorimetry. Calorimetry is a technique used to measure that heat transfer between a system and surroundings. You're going to actually calculate the value of Q. How awesome is that? A calorimeter, such as the picture here on the right-hand side, is the device that we can use to help us measure that heat transferred between system and surroundings. A very simple and inexpensive calorimeter can be a styrofoam coffee cup. Basically, you want your calorimeter to be as isolated of a system as possible. You don't want any of the air out here getting inside that cup. That way, all heat transferred from whatever's in the cup, the system and the surroundings in the cup, stay in the cup. We are going to be using a calorimeter in our virtual lab. We're going to put some metal and some water over here. You're going to heat it to about 100 degrees Celsius. You're going to take the hot metal and you're going to transfer it into this calorimeter. This is a little bit fancier one, isn't it? It's a virtual lab. We can spring for the more expensive calorimeter. So of course the calorimeter would not have the cap on at first. So you'd have it open, you'd pour that hot metal in here, and this calorimeter already has cool, just regular room temperature water in it. We have cool water in this calorimeter on the left, and then you're going to take this hot metal, you're going to pour it into that cool water, you're going to put the lid on it, and then you're going to put a thermometer in there so we can measure how the water changes. Think about what's going to happen. We have cool water in here. We're going to dump this hot metal in there and we're going to close it. What do you think is going to happen in that calorimeter? What temperature changes are occurring? What is your system? What is your surroundings? Pause and think about that for a moment. The hot metal is going to transfer its heat to the cool water. Eventually, both the cool water in here and the hot metal will reach the same final temperature. So in this lab, what is the system? When we're looking about just the calorimeter, and keep that in mind when you're doing the lab and all the calculations in the lab report, all we care about in terms of data, for the most part, is temperatures inside this calorimeter. What temperature was the metal when we first put it in here? What temperature was the water in here? What is the final temperature of this mixture? In this calorimeter, what is the system? What's the surroundings? And then I would like for you to explain the value of Q for each. Is the system going to have a positive Q or a negative Q? Pause this recording, rewind to the last slide if you need to, and then hit resume when you're ready. The metal is the system. The metal is what we've heated. We're putting in that cool water and we're seeing what happens. So the metal is going to be the system. The surroundings are going to be the water that's in this calorimeter. Now for the value of Q, since we are putting the hot metal into the cool water, the metal is going to lose energy. Therefore, the metal is going to be negative. The water is going to have a positive value of Q, because water gained the energy. It increased its energy. Therefore, it will have a positive value. So the positive Q of our surroundings will equal the negative Q of the system. So if we do a calculation and let's say calculate how much heat the water gained, well then we know how much heat the system lost, right? Because let's say the water gained 500 joules of energy. Where did that energy come from? Came from the hot metal. If the water gained 500 joules of energy, the metal, the system, had to lose 500 joules of energy. We just have to remember law of conservation of energy. That is it for our concepts. I hope you've learned a lot, reviewed a lot. We are going to have a recording over the lab, so if you get to the lab and need some help, click on that recording for 603 lab and we're going to walk you through it. Thank you so much and have a great day.